Hello folks, Mr. Whipple here. In this video we're going to be exploring the inverse trigonometric functions as the title is showing. Don't be surprised if in the middle of the video it asks you to answer a few questions before you can move along. You should also have the class notes and examples sheet from section 7.8 in front of you where you can take notes and be filling in blanks when you see the prompts for that. The story of the inverse trig functions resembles very much the story of any inverse function. Where did minus come from? Where did division come from? Where does a square root function come from? Why does it exist? Okay, and it all kind of starts with the fact that we needed to be able to undo some other operation. The square root exists because we need to be able to solve an equation such as this one, right? Where x squared equals 9. We need to be able to get rid of that square and be left with an x. So we came up with this function called square root, and when we square root both sides, we should end up with our solution. Okay, but let's take a look at how the square root function developed. I'm going to go to a new slide and start by graphing just y equals x squared. So here's our function y equals x squared. And we know that if we want to get its inverse, we need to simply switch, right, the input and the output, switch the x's and y's. That's what we learned back in first semester. So when we go about the business of literally switching the x's and y's, right, we might have -2, 4 on our original graph. We're going to end up with 4, -2. And if we do that to every point, we end up with a graph that looks like this, right? And this is all fine, except once we look at our graph, we can see we do not have a function. So if we actually want to have what's called the square root function, we have to find a way of limiting the range of our inverse so that we do have a function. And I think you guys know we decided to eliminate all the negative values, right, from this function, from this graph, so that we would end up with a function y equals the square root of x. So if we come back to our original problem, we know now that if we just take the square root of both sides, we're actually not going to have all the answers, right? We've seen this before. We need to make sure we take the plus or minus square root, which is actually applying two functions to our equation to solve, and then we have all the solutions, the two solutions. All right, so we're going to see something similar today as we approach all the inverse trig functions. So what do we need to be able to solve cosine of t equals 1/2, right? We need a new function that will undo that, right? So that when we apply that function to both sides of our equation, on the left-hand side, it's just going to leave us with our angle, which I'm letting being represented by t. And then we know that an angle that's got a cosine of 1/2 is going to be pi/3. But we've already seen this is actually not sufficient to give us all the solutions, right? We know that we need to be looking for the other places where the cosine is equal to 1/2. So first of all, right, we go ahead and add plus 2 pi k. And then we also look for the other place on the unit circle that has the same x-coordinate, try to draw a unit circle, as pi/3, and that would be down here, right, in the fourth quadrant. So we're looking at 5 pi over 3 plus 2 pi k. All right, so let's take a closer look at this inverse cosine function and see if we can define it as a function. I decided to go with units here for the grid marks on our graph, but you can see I've put in here, about 1.5 is where pi/2 would be, right? And a little bit beyond 3 is where pi is, and then you got a little bit beyond 6 is where 2 pi is. But take the points that are on this curve, right, and use those to help you sketch the inverse of this cosine curve right here. Why don't you pause the video and give that a try on your own graph paper. And you can just sketch the inverse function right on the same axes as your cosine function. All right, check and see if this is what you got. If you faithfully switch the x and y coordinates of each point, and of course you can just kind of pick the main points here to do that too. You know, like so here I know I'm going through 0, 1, so I make sure my graph goes through 1, 0. Right here I'm at pi over 2, 0, so I'm going through 0, pi over 2, and so on and so forth. And you should kind of see you basically have your cosine curve doing to the y-axis what it normally would do to the x-axis. And that is the inverse. All right, but of course, as we look at it, we can see that this inverse is not a function, just like we saw when we got the inverse of x squared. So we need to restrict the range on our red graph, our inverse function, somehow, so that we end up with a function. You may recall back in semester 1 when we wanted to sketch inverses of graphs on the calculator, we could do it using parametric mode. And so you can see here I've got the cosine curve sketched by just letting x equal t, and then y being the function we want. And if we want its inverse, we literally switch the x and the y, and so now you kind of see the same picture we had on the previous slide. All right, so our job now is to do something about this red curve so that it is a function. We need to restrict its range, all right? And we actually have some guidelines, as you can see on your, when you look at your class notes and example sheet at the top. There are guidelines for limiting the range of a relation to create a function, all right? The first guideline is that we want to keep the output values near the origin. All right, so fill in origin there. Get some dots here. The second guideline that we'll go by is we want to keep the function continuous. All right, meaning no breaks in the graph if possible. So continuous. I think I spelled that right. And then the third thing is we would like to use positive output values if there is a choice, okay? The order in which we try to apply these guidelines is in the order you see them, okay? So most importantly, let's try to keep our output values near the origin. Secondly, let's try to keep the function continuous. And then at the end, if we have a choice, let's try to use positive output values. So take a look at the red graph and see if you can come up with a range that would make this a function. You can see our graph paper now is in terms of pi, so every line is a pi over 2. All right, so like this would be pi right here, and down here we got negative pi over 2. This would be negative pi. So you can kind of use those lines to help you come up with your range. All right, and there should be a prompt for you to actually choose an answer on the screen. Okay, so let's take a look at the definitions of the inverse trig functions. You can see the first box here is for inverse cosine, and let's fill that definition in. It's going to look should look similar to other inverse functions that we've defined, but just kind of starting here, t is equal to the inverse cosine of y. So this is kind of a new function we're defining, if and only if, and what are we going to fill in there? Well, let's just solve this for y, right? So we're going to have y is equal to the cosine of t, right? And now here's where we set that range. So let's see if you got the answer right. It should be from 0, where 0 is less than or equal to t, which is less than or equal to pi. That is the best way to have values that are close to the origin, okay? Keep your function continuous. Meanwhile, also making sure you have a function, right? And then also using positive values. So hopefully that's what you said. All right, now this next line here is actually, we're just going to repeat what we wrote. It's just we're going to learn there's a new word that we have for inverse cosine, and that is, I should probably put parentheses around the t values. There should be parentheses around this y over here. Okay, but this new word is what we call arccosine. Okay, I think the reason we use another word to mean the same thing as inverse cosine is because you may recall we had some issues with this notation here with the looks like this is an exponent, but it's not. So one way to get around that is to use arccosine. All right, and then of course we're just going to fill in from 0 to pi as well. So these two things are saying they're the same definition, just using different wording. This next sentence gets to the heart of, do you really understand what an inverse cosine is? All right. So what we have involved here, right, if we go back and look maybe at this equation, is we have an angle, right? T is our angle, and then we have our y, right? And we might recall when we've been working with trig ratios before, we always take the cosine of an angle and we get a ratio. All right, so what is inverse cosine of y? Is that the angle or is that the ratio? I want you to pause the video and see if you can fill in these blanks, okay? Yes, do that now. All right, see if this is what you wrote. Does this make sense? That the inverse cosine of y is the angle. All right, if you look at it, right, what did we say inverse cosine was equal to? It's equal to t, right? And t is the angle. So inverse cosine of y is the angle between 0 and pi for which the cosine ratio is y. That's right, the ratio is y, right? Isn't that what we have, right? Here, let me write what we've written many times before. So we've always said the cosine of an angle equals a ratio. So the inverse cosine of a ratio is equal to an angle. So y is that ratio, right? That's the input now. Okay, and the last thing we just want to do here is sketch a graph now of the actual inverse cosine function and then write its domain. I've drawn my axes, and now all I have to do, right, is sketch the graph from this point at 0 for the range up to pi for the range. So it's basically going to start at 1, 0, whoops, cross the y-axis and end right there. And of course we want to mark that this is at pi, and we could also mark the y-intercept, of course, is at pi over 2. And then the other things we need to mark are our domains, right? We need to mark what these x values are. So answer the prompt and then fill it in on your paper. All right, hopefully you said that the domain is from -1 all the way up to +1. I'm using the interval notation. Of course, you could use inequalities for that. That would be a single compound inequality. What? -1 is less than or equal to x, which is less than or equal to 1, right? We are including those endpoints. Okay, so let's, we're going to do the same thing now for the other 5. We'll try not to spend as much time now that we've dealt with the cosine. There's going to be a fair amount of repetition. I have another prompt for you. Here, of course, is the sine curve, and the inverse sine is looking like this. So how would you restrict the range of this red function so that it is a function using our guidelines? So if you selected the correct prompt, you should have had here, let's see, by our definition, we're going to have that t equals the inverse sine of y if and only if y equals the sine of t, and we want to make sure t falls somewhere between -pi over 2 and +pi over 2. So we have that written in both spots here now. All right, and let's see, just like we said with inverse cosine, inverse sine of y, that is the angle, right? It's the angle between this time negative pi over 2 and positive pi over 2, for which the sine ratio is once again y. All right, and as far as sketching the graph, why don't you pause the video, see if you can sketch the graph, and then fill in the domain for inverse sine. All right, see if this is what you got. Of course, this time we want to be focusing on the part of the graph. Let's see, maybe drawing it would be good, right? We want to cut out, we're cutting our graph off here and here. So that's the part we're going to sketch. Over here, we're just going to go from negative pi over 2 to positive pi over 2. Probably what would be a good idea, too, is for me to actually delineate endpoints here. That's always a good idea. So we know we're including those endpoints. All right, and then you can see our domain is from -1 to +1, as it says down here. All right, let's move on quickly to tangent. I didn't draw the actual tangent function this time because you can imagine it would get quite confusing here, but you might recall the tangent function kind of comes up and has vertical asymptotes, right, at pi over 2 and negative pi over 2, so it should make sense now that we have horizontal asymptotes at negative pi over 2 and positive pi over 2, and the graph is still doing this repeated pattern, just doing it horizontally. All right. One thing I might impress upon you so that we can kind of know this is the correct way the graph is working. When we think about inverses, remember we're talking about switching the x's and y's. All right, so if we're looking at the original tangent function, I'll point out that, let's see, of course we know it looks like this, and I'll point out that its slope, which would be delta y over delta x, I'll point out that its slope is positive, right? It's a positive slope. So what's going to be true about the slope of the inverse function? Is it still going to be positive, or might it become negative? Is it possible that can happen? And if you think about what we're doing with inverses, you can know for sure that the inverse, the slopes of the average rates of change, maybe is what the word I should be using, that those are also going to be positive, right? Because when you switch x and y, that doesn't change whether, that doesn't change the SIGN, the sign of the slope. So we can kind of know that the inverse tangent is also going to be increasing as it goes between the horizontal asymptotes. All right, so here's your prompt. How would you restrict the range of this red function so that it is a function, right? Because obviously right now it is not a function. So answer the prompt and then we'll continue. All right, so if you got the correct range, you should have t equals inverse tangent of y if and only if y is the tangent of t, and t must fall between negative pi over 2 and positive pi over 2. I will point out this time they're not equal, like in sine, right? Because we have those horizontal asymptotes there. We're not going to actually have values at pi over 2 or negative pi over 2. And then, of course, same thing is true. We call this the arctangent function. All right, and the inverse tangent of y is the angle between negative pi over 2 and positive pi over 2, for which the tangent ratio is y. And why don't you pause the video, see if you can sketch the graph of the function arctangent, keeping in mind that we're going to, we've decided to stay between negative pi over 2 and positive pi over 2. And then fill in your domain. All right, see if this is what your graph looks like. All right, so we just do the portion of the graph that we were talking about. And yes, the domain is all real numbers this time, right? Just like the range on the tangent function was all real numbers. All right, let's take a look at, we got three of the reciprocal trig functions left. Let's take a look at them. when you think about the fact that the inverse cosine graph kind of does this kind of thing, then it can maybe make sense why the inverse secant graph is doing what it's doing, right? Doing the opposing horseshoes horizontally. Now, let's see. When it comes to the fact that we don't have a function and we need to restrict our range, you're going to see that one of the guidelines is going to get broken. We're going to have to actually not worry about the continuity piece, okay? Because if we keep continuity, if we did an entire one of these horseshoes, we wouldn't have a function, okay? So we have to break it right there and go with, say, that piece, and then so that we also take into account all the x values we can have, we're going to come over here and grab this piece right here and stop it right there. So keeping our values positive. So if you look at it, this the arcsecant actually has the same range as t equals the inverse cosine, okay, which is kind of nice because we do associate, let's see, this would be inverse cosine of y, because we do associate cosine with secant, so they do kind of stay together here. All right, so that's one way you can remember that the inverse secant has the same range as the inverse cosine. Likewise, the inverse cosecant is going to have the same range as the inverse sine, right? As inverse sine of y. Let's see if it's going to let me write this in here. I'm having a time with my pen a little bit. Inverse sine of y. Come on. There we go. Yeah, and you can see the same kind of thing is happening with that. We have to kind of chop it off right here and right here so that we get all the possible x values we can in there, still have a function, but we're not going to have continuity all the way through the graph. Now we could, if we wanted to, try to keep the inverse cotangent range the same as the inverse tangent. It's possible it could work, right? We could chop it off right here at negative pi over 2, include that piece, chop it off right here at positive pi over 2, include that piece. But then two of our guidelines would be broken, right? We wouldn't have continuity. We also wouldn't be using positive values on our range. And so we can achieve both of those guidelines if we go up here, okay? And so it turns out that the inverse cotangent does not have the same range as inverse tangent. So that pattern is broken there. Here, I'll just write that in here. So this would be inverse tangent. But keep in mind, this is a knot. They don't have the same range. So what is the range of cotangent, right? Cotangent is going to go from 0 up to pi, right? It's just going to be this curve right here. All right, so let's write that up and then we will be done. All right, so just to finish up here, we can see we can fill in our definition. We are going from 0 up to pi for inverse cotangent. Notice it's not equal to, right? Because we have those asymptotes, just like with inverse tangent. All right, and we fill in, we got angle between 0 and pi, for which the cotangent ratio is y. And when it comes to sketching our graph down here, right, I'm just sketching this piece of that curve. Now, how can we kind of remember that it's decreasing is, remember, keep in mind that the cotangent curve decreases and the inverse will still decrease. That goes back to that slope being delta y over delta x. If you switch the x and y, I have delta x over delta y, you're not going to be changing the sign, right? So, we're talking delta x over delta y still keeps the SIGN negative. All right, and so let's see, I forgot to write our domain, but just like it was with tangent, the domain is all real numbers. All right, well, that concludes this video. I hope it didn't seem too long, and since you had to be involved as well. The next step will be to look at the rest of this class example sheet and start to determine what certain values are, like what is the inverse sine of 1/2? Could you say it's equal to 5 pi over 6? Maybe so, maybe not. We'll take a look.